Okay, this is number 1. And you notice you have x cosine squared theta plus x sine squared theta. Just algebraically, what do you think you can do to this? This is x times something plus x times something. Factor out an x. So hopefully you saw that. If I factor an x out, we're going to have a cosine squared theta plus a sine squared theta, right? Now what? You can't factor a theta out, and here's the reason why. Because if you had, say, a function, you can't, see, these are just functions, these are numbers. And so you can't necessarily factor a theta out because it's not theta times cosine squared, it's the cosine squared of a theta. So that's why you can't factor those. Yes?
Factor out the squares?
You can't really factor out a squares either. It's just like when we do the x plus y quantity squared, you can't just factor a squared out. It's even easier than that, and it's something that we've been working on a little bit. And once you see it, you're going to go, oh, that's really easy. Does anyone remember what cosine squared plus sine squared equals? 1. Guess what? That's 1. Not even 1 theta. It's just 1. Because we had shown the other day that any time, it doesn't matter what angle you put in there for theta, if you have cosine squared of that angle plus sine squared of that angle, it equals 1. Every time. So guess what? That's out, 1's in, and now your final answer is just x. That's a lot better. Okay. Now on B, that's a little trickier. We'd like to be able to do maybe the same thing, but we'll see if it's possible here. You can go around that. Yes.
You have the two x cosine squared thetas together and you get 2 x cosine theta.
Exactly. Sometimes when you see these things, there's too many variables here to really think. But this is just one term. X cosine squared theta. X cosine squared theta. That's the same term. So how many do you have, Carl?
2.
2. So that's 2x. So that equals 2x cosine squared thetas from those two.
So you can factor out 2x.
Plus the 2x sine squared theta. And now we can factor out the 2x, just like we just did.
And then cosine squared plus sine squared.
Exactly.
Is 1, so the answer is just 2x.
Exactly. So you have just cosine squared theta plus sine squared theta. That's a trig identity. It's called a Pythagorean identity because if you remember what we talked about yesterday, we can make that on a unit circle and it gives us Pythagorean theorem. That's just substitute a 1 in there because it's equal to 1. So the answer is 2x. Okay, so what they're trying to show you here is that, I don't say they're trying to show you, you've already seen, but it's how can you use that cosine squared plus sine squared. And the way you can use it is anytime you get that, you can substitute a 1 in, and that's okay. Questions there? Now in this one, we have a triangle. We have a 72-degree angle, so I'm going to draw hopefully a good picture here. A 72-degree angle. Not going to be perfect. Okay, we'll take a 72-degree angle. And we have a 12-centimeter segment is making the 72-degree angle with a 16-centimeter segment. And we want to find the length of this third side. Okay, we did a problem like this yesterday. You can see it on the board there. But they drew the altitude in there. So let's do that. We're going to draw the altitude in, kind of making an opposite side from the 72 degrees. That's kind of the key here. So if we want to find the area on the second problem, and we want to find the third side, what do you think we're going to have to find here? What do you need to find the area of a triangle? The height, the base and the height. We already have the base. There's the base. We need the height. So how are we going to find the height here for this one, for this triangle. Yeah, so we need to find this, and can I use h? Are you okay with that?
Sure.
So it's height. So we can do sine 72 equals h over 12. Right? And if we do that, what does h equal?
Sine 72 times 12.
Yeah, 12 times sine 72. So now we have what h equals.
Do you not want to solve?
So Tom says that 12 sine 72 equals 11.41 centimeters for the height there. So I'm going to write that here. Now, to find the third side, here's a method I'm looking at. I want to find this third side. What kind of triangle is this right here? Right triangle. If this is a right triangle, my goal would be to find this side. If I can find this side right here, this piece, then what could I use to find this third side? Pythagorean theorem. So if I already have the height now. I'm going to have to use this. So I can't really find this because I don't have any other information. But, yes, Alex.
Square root of 12 squared minus 11.41 squared.
So you're saying to find this side first? Sorry, Amanda, was that going to be your thunder? Now here's the question. Would you do it? He just said he wants to use Pythagorean theorem to do this. All right? Were you going to do that same thing, or you're going to do that? What else did you say? What did you say, Tyler?
I said tan 72.
Now here's the thing. You could use tan. What else could you use?
Oh, never mind.
To find this side, what else could you use? You could use tangent and cosine. I'm going to use cosine here, and here's the reason why.
Because you don't know if the 11.41 is right.
Yeah, I might mess up. So, I'm going to call this side little a here. Okay, and to find little a, I would use cosine 72 equals a over 12. So what does a equal? 12 cosine 72. Tom, where are you? Yeah, you. 3.71? I believe you. Cautiously, but I'll believe you. Oops, I just put 7.2. 3.71. Okay. So now I have 3.71 there. So how am I going to find this side now? Subtract it. So 16 minus 3.71 is 12.29. Then, like we said, we can use Pythagorean theorem to get this side. We'll call it C, of course, Pythagorean theorem. So we can go C squared equals 11.41 squared plus 12.29 squared. And what do we get for C there?
I didn't do Pythagorean theorem, but I got
16.77. Does that sound right? Yeah. So you didn't use Pythagorean theorem. So what did you use?
I made it harder than it needed to be. I found the angle of that far one opposite of, no, not that one.
You found this angle?
Yeah, that one.
Okay.
And then I used
A trig function.
yeah,
How did you find that far angle?
I did the inverse tan of 11.41
Ooh,
over 12.29.
I like it. I'll put that on here too. Or you could have used arctan 11.41 over 12.29, and that would find this angle right here. And then from there, use a trig function to find C. I like that too. Okay, so lastly, we have the area. So the area will be 1/2 base times height, or 1/2 11.41 times 16. And what'd you get there, Tom? 91.28 square centimeters. All right, this is number 4. And I can tell you right now, it's starting to build us into what's called the law of cosines, which I think is on the next page, but I didn't assign it. So I want to talk about that too. The first step they want you to do here is express CD in terms of angle B and side A. And we've been working on this. So here's angle B, here is side A, and here is CD. Okay, so how are we going to write one equation for that? Yes?
So if you kind of like isolate that triangle,
Right.
assuming CD is the end,
Mm-hmm.
you could use sine.
Perfect.
So
Yep.
Yeah, opposite over hypotenuse.
So sine B.
Sine B equals CD over A.
I'll go back on B.
Okay.
Okay, so yeah, here's B. We can use for CD, and we have A, so we're going to do opposite over hypotenuse. It wants us to express CD in terms of those, so we could do CD equals A sine B. So this right here would be A sine B. Okay, B. Express BD in terms of the same two pieces. Jacob.
You could do cosine B equals BD over A.
Cosine B equals BD over A.
And then add or multiply the A either side, which is BD equals A times cosine of B.
BD equals A cosine of B. I'll box that top one, that's bugging me now. So now we have A cosine B. All right. And now it says to simplify the expression A sine B squared plus A cosine B squared and discuss its relevance to the diagram. So, what does this have to do with the diagram? Yes, Tom.
Equals A.
It equals A. So, you're close, I think.
No, it equals A squared.
A squared. And why does it equal A squared?
Because
Squares on the
it's
outside.
squaring the whole thing.
Right.
Just
I knew that.
cosine B.
Yeah, so if we just look straight at this right here, we just did a warm-up on this a second ago, but you would get A squared sine squared B plus A squared cosine squared B. I know it's getting ugly over there. I could factor out the A squared, and the rest of it is now this is where you start getting lazy, sine squared B plus cosine squared B, just knowing that those aren't C's, they're sine and cosines. And that equals 1, so it's A squared. And how does that relate to this diagram right here? What does this have to do with that? What's that?
I don't know what you just said.
What does this have to do with this? There's one term I'm looking for. Pythagorean theorem. That's a Pythagorean theorem for this. If I square this and add them together in this right triangle, I'll get A squared. Okay? And then the last question, D, it says, why was A sine B used instead of sine B A? Yes?
So if you had done sine B times A, then what you would have been doing is multiplying B times A and then finding the sine.
Exactly. we always want to put, since we're not multiplying it just by b, you want to put the a out in front, so that way you're multiplying a times sine b, not just times the b itself. Okay, I took the triangle we had from the previous problem, and I just added this whole length as c. And the reason I'm calling this whole length c is because you usually call it lowercase c for the side across from the angle c. So that's why I called that little c. Okay, and this little a, see how little a is across from angle b or angle a. And then we can call this last side b. So we'll call this lowercase b because it's across from the angle b. So the question is, can we come up with a formula when you're given, and we just did a problem like this without a formula, but when you're given a side, angle, side, so you're given these three pieces, can you solve for this third side? That's the goal here. So we're pretty close. We're pretty close so far. We're going to need a little bit more. So I want to solve for in terms of b. So if you remember on number 2 and 3, we want to solve for b. What do I need the length of to solve for this? I have CD. I need AD. I need this length right here, right? Because we use Pythagorean theorem to get that length. So what would this length right here be? What would AD be? And it's pretty simple. Just look at the purple. C minus A cosine B. Okay? So now what we want to do is we want to solve for B in terms of these. So it's actually pretty nice here. I'm going to make it a little smaller. I'm going to go color here. Okay, so if I want to use, and we just did this a second ago, if I want to find B here, and I use Pythagorean theorem, help me out, I would do B squared equals, yeah, so it'd be, I'll just do this first though, A sine B squared plus C minus A cosine B squared. And now hopefully you'll be okay with how I'm going to simplify these, because we did this yesterday on a warm-up, these types of problems. So this would be A squared sine squared B, right? Now this one we have to distribute. So when you distribute, you're going to get C squared minus, actually I'll do this. I'll do what you guys usually do, plus A squared cosine squared B. Now I'm forgetting something, and what am I forgetting?
To make the other terms
We
negative.
need another term here, because what you guys ought to do sometimes is a mistake that a lot of students make is they'll just do this squared and then this squared.
Minus 2A cosine B.
You have to multiply these together and double it. So that would be minus 2AC cosine B. Okay, and again, that's from the idea that if you have x plus y quantity squared, that's x squared plus 2xy plus y squared. Okay, so now this is looking pretty ugly. If somebody came in right now and looked at this, they go, wow, you guys are so smart. This is what you're doing, because this is crazy. So what do you notice? Do you notice anything about the terms here? We have an a squared sine squared b, a c squared, an a squared cosine squared b, and then this. Pythagorean theorem. What do you mean? Right, but I want to do algebraically. What can I do here? Look at these two terms. I can semi-combine them. I'm just going to reorder, and maybe you'll see this. And I'm going to go a squared sine squared b, and you got to remember what we've been doing today. A squared cosine squared b, And you see a 1 in there somewhere, right? That's, so far you're right. And then the c squared is left over, minus 2ac cosine b. And how can I make a 1 out of this?
Factor out a squared.
Factor out a squared.
So you get a squared plus c squared minus 2ac cosine.
And I'm going to do the longhand. I'll show you the whole step just so you see what I'm doing if you're completely lost. I factor the a squared out of that portion right here. And I'm just going to say, because I'm really lazy, I'm just going to say dot, 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 the rest of this. And then what's going to happen to that, what's in the parentheses here?
Becomes 1.
That becomes 1. So final answer, b squared equals a squared
Plus c squared
plus c squared
minus 2ac.
minus 2ac cosine b. Those of you in geometry, do you see where that came? Does this ring a bell at all?
Yeah.
Yeah.
Yes, this right here. This right here is the law of cosines.
It actually makes sense now.
And that's hopefully, at least if you've used it before, then it might make sense of where it came from. That's law of cosines. And what you use that for is now, let's say you're given, and we'll practice this on tonight's homework, I'm sure, but if you're given a side, an angle, and a side, like you were on last night's homework, and you want to find the third side, you can just substitute in side, the other side, the angle, and then calculator work and get the answer for the third side without having to do any other work. That makes sense?